I am Nguyễn Thành Nam, uh, Chu Chu BI 13325. I am group 4 and this is the exercise 2 data repre- representation. In exercise 1, inside magnitude notation, the leftmost bit represents the sign of the number, with a 0 indicating a positive number and 1 indicating the negative number. The remaining bit repres- re- represent the magnitude of the number. To find the sign magnitude of minus 3710, we first determine the binary representation of the absolute value of the number, which is 001000101, to obtain the sign magnitude of minus 3710. We simply flip the leftover bit from 1 to 0 to 1 to indicate the negative sign, giving us 10100101. Therefore, sign magnitude of minus 3710 is sign magnitude notation is 10100101. Exercise 2, to represent decimal value 2410 is sign magnitude notation. We follow this step. Write the absolute value of decimal number in binary magnitude equal to 00011000. Add a sign bit at the beginning of binary number, 0 for positive, 1 for negative. So we have positive 24 is 00011000. Then the 8-bit binary represent for decimal value 24 is sign magnitude notation is 00011000. To represent decimal minus 24 inside magnitude notation, we follow this step. While the absolute value of decimal number in binary therefore equal to 00011000 as a sign bit of beginning of binary number. So we have minus 34 equal to 1001100. Exercise 3. The size magnitude of minus 63 using 8-bit binary sequence is. So size the 63 in binary is 0 111 adding a negative sign being us a 101111. Exercise 4, filling the we will filling the empty slot in the table by converting the number into different representation. All the number are 8-bit in length. So in the first row, we can transfer binary number 00100001 to hexadecimal is 21p, and two-sided decimal is 33. In the second row, we have 6f in hexadecimal, so we have 0, 1, 1, 0, 1, 1, 1, 1 in binary and 1, 1, 1 inside decimal and 1, 1, 1 side the decimal and 1, 1, 1, 1 in unsigned decimal. So the third row we will use minus 92 and binary 1, 0, 1, 0, 0, 1, 1 0, 0. To have the hexadecimal is 84 and unsigned decimal is 164, and in the last row we will have the sided decimal is minus 25, so we convert it to binary. We have 1, 1, 1, 1, 0, 0, 1, 1, 1, so we use the binary to have the last is E7 and 2, 3, 1. The exercise 5, the F binary sequence is 1, 0, 0, 1, 1, 0, 0, 1, represent the decimal value 153 if the unsigned notation. If the sided magnitude notation, the first bit represents the sign and remain 7 bits represent the magnitude of number in binary. So 1, 0, 0, 1, 1, 0, 0, 1 represent minus 25 in sided magnitude notation. If this represents notation is in excess notation, we need to know the value of the bias to determine the decimal value. It represents the bias. It usually half of the maximum value that can represent by the number of bits used. For an 8-bit binary sequence, the maximum value is 255, so the bias would be 127, subtracting the bias from an unsigned value, giving us 153 minus 127 equal to 26. So 100110001 represents 26 in excess notation.
Okay, today we talk about the solution of the exercise number 6, number 7, number 8, number 9, number 10, and number 11. My name is Nguyễn Quang Minh. My student ID is 22BI1213299. So, with the first exercise, the decimal value 1110 can be presented using an 8-bit binary sequence in different notation. In unsigned notation, it would be presented as 01000110, and inside magnitude notation, it also will be presented as 1001000110. Since the first bit represents the sign and the remaining 7 bits will represent the magnitude of the number in binary. And in excess notation, we need to know the value of the bias to determine the binary representation. For an 8-bit binary sequence, the maximum value is 255, so the bias would be 127. With adding the bias to the decimal value gives us 1110 plus 127 equal to the 1237. However, this value is greater than the maximum value that can be represented by an 8-bit binary sequence 255, so it cannot be represented in access notation using an 8-bit binary sequence. So we see the solution, the exercise 6. Now we will move to the exercise 7. In this exercise, we need to understand that the 8-bit binary sequence 1000101111 represent different decimal value depending on the notation used. Number 1, in unsigned notation, this number represents the decimal value 139. So the second, in sign magnitude notation, this number represented minus 11 in sign magnitude notation. The third, in excess notation, this number represents 12 in excess notation. And the last in number 4, in complement notation, this number represented minus 117 into complement notation. So we move to the exercise 8. So to find the second complement of a binary number, we need to invert all the bits and add 1. Here the second complement of the given binary. In A, the second complement of 01101001010 is 10110110. It will be the second complement of 10010000 is 01110000. And with the number C, and with the C, the second complement of 10110110 is 101 010011010. And the last is the D, the second complement of 01110000 is 10010000. So we to the exercise 9. To assuming two complement notation and using only 8-bit, here the result of the given operation. In A, we plus to these two binary, and we will have the result of it is 11100110, and with the B we do the same, and we will have the result is 01100100. And with the D and E and F, we plus two number and have the result on the screen. You can see that, but the C is the except of them. So we will minus two number and is equivalent to the plus of to this number, and we have the result 100111100. However, since we are only using 8-bit, the leftmost bit is discarded, so we will remove some number, and the final result of this C equal to the 00111100. So next, on the above operation work correctly except the operation C. So the C operation result in an overflow which occur when the result of an addition of or subtraction operation is outside the range of values that can be presented with the given number of bits. Here we will written the given is 8 bit. Yeah. So in this case, the result of the subtraction is minus 60. We can present it using 8 bit in to complement notation. However, due to the overflow, this result is incorrect. Next, we will move to the exercise 10. So if the 8-bit binary bit pattern 10101010 is a true complement integer, it represents a negative number because the first bit is number 1. So to find its value, we need to invert all the bit and get and add number 1 to get 0 1 0 1 0 1 1 0, which is 86 in decimal. So 1 0 1 0 1 0 1 0 represent minus 86 into complement notation. And we move to the final exercise in my speech that the 11. So firstly, to find the unsigned fixed point binary present of the decimal number 128.125, we need to convert both the integer part 128 and the fractional part 0.125 to binary separately and then combine them. With the first part is the integer part. 128 can be converted to binary by repeatedly dividing it by 2 and recording the remainder. This gives us 10000000. Then with the second part is the fractional part, which is 0.125 can be converted to binary by repeatedly multiplying it by 2 and recording the integer part. This will give us the number is 0.001. So final, when we combine the binary representation of the integer and fractional part, give us 1000000.001, which is the unsigned fixed point binary representation of the decimal number 128.125. So thank you for listening to my speech.
To convert 101.101 from unsigned fixed point binary representation to decimal, we need to convert both the integer part 101 and the fractional part 101 to decimals separately and then combine them. The integer part 101 can be converted to decimal by summing the product of each bit and its corresponding power to 2. This gives us 1 times 2 power to 2 plus 0 times 2 power to 1 plus 1 times 2 power to 0 equal 4 plus 0 plus 1 equal 5. The fractional part 101 can be converted to decimal by summing the product of each bit and its corresponding negative power of 2. This gives us 1 times 2 power to negative 1 plus 0 times 2 power to negative 2 plus 1 times 2 power to negative 3 equal 0.5 plus 0 plus 0.125 and equal 0.625. Combining the decimal representation of the integer and fractional part gives us 5 plus 0.625 equal 5.625, which is a decimal representation of the unsigned fixed point binary number 101.101. Part B. To convert the decimal number 72.375 to unsigned fixed point binary representation, we need to convert both the integer part 72 and the fractional part 0.375 to binary separately and then combine them. The integer part 72 can be converted to binary by repeatedly dividing it by 2 and recording the remainder. This gives us 1, 0, 0, 1, 0, 0, and 0. The fractional part 0.375 can be converted to binary by repeatedly multiplying it by 2 and recording the integer part. This gives us 0.011. Combining the binary representation of the integer and fractional part gives us 1001000.011, which is the unsigned fixed point binary representation of the decimal number 72.375. And move to the next exercise. Exercise 30. To represent the positive point 0.8 is a given floating point representation with 1 bit size, 4 bit exponent, and 6 bit normalized multi-char. We need to convert the decimal number to binary and normalize. The decimal number 0.8 can be converted to binary by repeatedly multiplying it by 2 and recording the integer part. This gives us 0.110011001100, and so on. To normalize it binary number, we move the binary point to the right of the first non-zero digit and adjust the exponent accordingly. It gives us 1.10011011000 times 2 power to negative 1. The sign bit is 0 because the number is positive. The exponent is negative 1. We need to represent in excess notation with a bias of 2 power to 4 minus 1. Minus 1 equals 7. So the exponent field is 0, 1, 1, 0. The multi-char field is 1, 0, 0, 1, 1, 0, which is obtained by truncating the normalized binary number after the first 6 digits. For the part B, to convert the floating point representation back to decimal, we need to convert each field to decimal separately and then combine them. The sign bit is 0, so the number is positive. The exponent field is 0, 1, 1, 0, which represents the 6 in decimal. Subtracting the bias of 7 gives us an exponent of negative 1. The multi-char field is 10110, which represents 1 times 2 power to negative 1 plus 0 times 2 power to negative 2 plus 0 times 2 power to negative 3 plus 1 times 2 power to negative 4 plus 1 times 2 power to negative 5 plus 1 times 2 power to negative 6 and equal 0.40625 in decimal. Combine the value give us 0.703125, which is the decimal value represented by the given floating point representation. The last part. The relative error of this representation can be calculated as 0.8 minus 0.7033125 divided by 0.8 and equal 0.1210937 Exercise 14. To convert the 32-bit floating point hexadecimal number 3EA0000 to its decimal value using the IEEE 754 standard with 1 bit size, 8 bit exponent, and 23-bit multi-sum. We need to first convert the hexadecimal number to binary and then extract the field. The hexadecimal number 3EA00000 can be converted to binary by converting each digit to 4-bit binary representation. So it gives us 011, 1110, 101010, 000, 000. The side bit is the first bit which is 0, so the number is positive. The exponent field is the next S bit which is 0111101, representing 125 in decimal. Subtracting the bias of 2 power 2 8 minus 1 minus 1 and equal 127 gives us an exponent of -2. The multi-sharp field is remaining 23 bits, which is 1 which is 0, 1 and 0000000 and so on, representing 0 times 2 power 2 -1 plus 1 times 2 power 2 2 plus 1 times 2 power 2 -3 and on the way to 0 times 2 power 2 -23 and equal 0.25 in decimal. Combining the value gives us positive 1 times 2 power 2 minus power 2 -2 times 1 plus 0.25 and equal positive 0.3125, which is the decimal value represented by the given floating point hexadecimal number.
Exercise 15 to present minus 1.5625 multiply 101 with IEEE 745 standards. We can close this step. One, determine the size of the number. Size the number is if the size bit will be 1, 2, convert produce 1 uh, 56 25 multiply 100 100 101 to binaries the integrals part of the number is 1, which is printed as 1 in the binary to convert the fractional part of the number 1.5625 to binaries. We can use the following process: 1.5025 multiply to equal 1. 125 one 0 point 125 125 multiply 2 equal 0 point 0.25 uh, 0.25 multiply 2 equal uh, 0.5 0.5 multiply 2 is same one. The battery representation of the factual fractional parts is uh, 1 million 1 million one. uh, therefore the battery representation of the entire number is 1.1 million point one. 1 million 1 million one. Just three normally normalize the binaries representations. Side we have a binaries points after the first type is we can shift the uh, decimal points to the left until we have one before the binary points. In this case, we can shift the uh, decimal points to place to the left, give us 0.11 um, 0.001 plus multiply uh, 100 uh, 103. Yes. Next, for determine the exponent. The exponent is the number of place we can shift to the uh, decimal point to the normalize binary representations. In this case, we shift to place to the left, so the exponent is 3. Convert the exponent to the uh, binaries and as bias the bias of a of an 8 bit 8 bit exponent is 122 27. Yes. uh, therefore therefore we need to add uh, 127 to the exponent to get the final exponent value uh, in binaries 3 point 3 plus 120 122 20 27. Yes. Is same 10 10. Yes. Maybe like uh, this is value. Compile this side exponent and uh, multiplier to the final bit uh, factors. The side bit is 1. The exponent is uh, 0 1 0 0 0 0 0 1 0. And the multiplier is 1 0 0 1 0 0 0 0 and 0. Uh, we therefore the final bit balance is actually 1 0 1 1 0 0 0 0 0. We you can see this number in the PowerPoint, in my PowerPoint, yes, in my presentation. Next is next is exam um, 16. Is one is a plus one for 0.5 for 0.5 plus 0. Uh, 32 31 22 we can follow the this step uh, in A the converse 0.5 to the binaries 0.1 converse 0.32 31 25 to binaries 0.010. uh, the binaries value of the operators are 0.5 is the same 0 0 0 0 1 1 1 1 1 1 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 22 it's a uh, 24 number 0 before after uh 0.31 is 0.11111101 1 2 3 4 5 6 7 8 11 12 13 16 18 21 21 number 0 absent. It is a B um, apply the binaries points as and add the matrices matrices. Maybe you will see in my presentation. I cannot do this season. The this this number about the add, analyze the binaries points and add the matrices. Yeah, here. The result of the addition is 0.8125. Let me see. Normally normalize the result 0.8125 say it's same 1.2 multiply multiply 2 uh, to have minus 1 the normalized binaries re representation representation is uh, this number this here. That is a value in exercise 16 we follows 12 minus 3 3 uh, 3 875 we can follow this set in A the converse is 12 to binaries is 100 mm, 1 billion 1 million 1 billion 100. The converse 3 8 uh, 875 to the battery is 1 11 point 111 the billion the binaries uh, value is for the operators are 20 is the same year this yeah and 800 simplify is same this number. Okay. Next B analyze battery points and change the material this number. Research of the suggestion uh, is at the normalize the result at uh, at equal 150 multiplied to cut 3 the normalized plenaries representation is this number.
Okay, so in 17 exercise, to convert the ASCII string of 9.75 to its hexadecimal representation, we need to convert each character to its ASCII code and then represent that code in hexadecimal. So the ASCII code for the character 9 is 57, which can be represented in hexadecimal as 39. The ASCII code for the character point is 46, which can be represented in hexadecimal as 2e, and the ASCII code for the character 7 is 55, it can be represented in hexadecimal as 37. The ASCII code for the character 5 is 53, which can represent it in hexadecimal as 35. The new the lunar terminator has an ASCII code of 0, which can be represented in hexadecimal as 00. So the hexadecimal representation of the non-terminated ASCII string 9.75 is 39 2e 37 35 00. Okay. Moving on to exercise 18. So to convert the given binary code into an ASCII string, we need to divide it into 8-bit chunks and convert each chunk to its corresponding ASCII character. The first 8-bit chunks is 0, 1, 1, 1, 0, 0, 0, 0, which represent 112 in decimal. The ASCII character with code 112 is B. The second 8-bit chunk is 0011000001, which represent 49 in decimal. The ASCII character with code 49 is 1. The third 8-bit chunk is 00110011, which represents 51 in decimal. The ASCII character with code 51 is 3. The fourth 8-bit chunk is 01110011, which represent 115 in decimal. The ASCII character with code 115 is S, and the final 8-bit chunk is 0, 0, 0, 0, 0, 0, 0, which represent the null terminator. So the given binary code represent the null terminated ASCII string is P13S. In exercise 19, in the A part, it if a color display use 8 bits for each of the primary colors, which are red, green, and blue per pixel, and has a frame size of 1218 multiplied by 1024, and the minimum size of bytes of the frame buffer to store a frame would be calculated as follows. So each pixel requires 8 bits for each of the 3 primary colors, for a total of 24 bits per pixel. So the total number of pixels in frame is um, 1310720 pixels. Therefore, the minimum size of bytes of the frame buffer to store a frame is 1310720 pixel multiplied by 24 bytes per pixel. And okay, so the minimum size in byte of the frame buffer to store a frame is 1310720 pixel multiplied by 24 bytes per pixel per 8 bits per byte is 3932160 bytes. So the B part, if the frame buffer has a size of 3932160 bytes and needs to be sent over a 100 megabits per second network, then the minimum time it would take to send the frame would be calculated as follows. The size of the frame buffer in bits is 3932160 bytes multiplied by 8 bits per byte, which equal 3145728 bits. Therefore, the minimum time it would take to send frame over a 100 megabit per second network is 0.314572 seconds. In exercise 20, even the two 16-bit numbers expressed in hexadecimal representation XABCD and XFEED, we can evaluate the expression XABCD and not XFEED as follows. So first we need to convert the hexadecimal number to binary. So XABCD can be converted to binary by converting each digit to its 4-bit binary representation. This gives us 10, 10, 11, 11, 11, 11, 00, 11, 01. So XFEED can also be converted to um, binary as 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1. Next, we need to apply the NOT operation to XFEED. This gives us 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. Finally, we need to apply the AND operation to XABCD and not XFEED. This given us 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1 and 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, which equal 0, zero 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 1 0 0 0 0 0 0 0 0. Converting this binary result back to hexadecimal gives us x 0100. So the result of the expression is x 0100.